Welcome to lecture 26. In this lecture, I will talk about circular closed orbits, and I will compare the results in general relativity to the Newtonian theory. First, recall that we have found that the Schwarzschild solution is a solution to the equations of motion for general relativity. We discussed the Schwarzschild solution for a mass in outer space, and we derived the equations of motions for a massive particle in that Schwarzschild solution. So in this lecture, I want to specify the motion that we want to consider. Namely, we want to consider circular orbits for a particle in the Schwarzschild metric. And you can think that this is equivalent to having, for instance, a satellite orbiting Earth or something like this, because the Schwarzschild solution is giving us the gravitational field of a body in empty space. And then we have some test mass, and we'll consider circular orbits of this particular test mass. When we do so, we will find solutions to our GR equations of motion for this circular orbit, and we can compare that to the corresponding result from Newtonian gravity. To get started, recall that in lecture 25, we found that there is an equation that connects the derivative of the radius of a particle with respect to its proper time to other properties in the spacetime, in particular the Schwarzschild factor that we called A, this is this factor here, and the conserved energy of the particle and the conserved angular momentum. If you look at this, then you should realize that this is very similar to a classical mechanics equation, namely the equation of an energy balance. Specifically, if you consider the energy balance of a classical particle with mass m and velocity v in a potential v of r, then Newtonian mechanics tells you that the energy of the particle is given by the kinetic energy plus the potential energy, and the kinetic energy is mv squared over 2, and the potential energy is mass times the potential v of r if the potential is only dependent on the radius r. Now, the velocity, of course, is, if the velocity is radial, then the radial velocity dr by dt is just this velocity v. So that in the Newtonian theory, we get, if we divide by mass both sides, that the energy per unit mass is given as 1/2 v squared, which is now dr by d tau, plus the potential v of r. And that is very similar to the GR equation that we found, which is some constant, which you can then relate to the energy per mass. So this E squared over 2 basically will have the interpretation of energy per mass. Then we have the 1/2 velocity squared term, which is the same. And then we have some term that depends only on r, which you can interpret as some kind of potential v of r. So the upshot is that in general relativity, there is an energy budget for Schwarzschild solutions that is similar to the energy budget in classical mechanics. The only potential difference between classical Newtonian gravity and full general relativity is then the particular form of the potential that is predicted by the general relativity equations of motions, which is this part here. Let's now compare this in more detail. To do that, basically, we have to write down the potential in Newtonian gravity. So if we have Newtonian gravity, then the gravitational potential away from a body of mass m is given by minus Newton g times m over the radius r. And if in addition the particle we are considering has some angular momentum, should I say it's the angular momentum per mass, similar to the energy per mass that we discussed before, then in classical mechanics, there's a potential energy term that's just angular momentum squared over twice the radius squared. So in the Newtonian theory, we find that the classical potential is the sum of the gravitational potential and the angular potential, angular momentum potential. And the sum of these two terms is just minus gm over r plus L squared over 2r squared. We can now contrast this to the potential that is given by the equations that come from GR. So this is this combination here, which was 1/2 Schwarzschild factor 1 minus 2gm over r times the term 1 plus L squared over R squared that came from the conservation of the killing vectors. So if we expand this expression and write it in a way similar to the classical potential in the Newtonian gravity, we find that indeed there are some terms that agree very nicely. So there's the gravitational potential part in Newtonian gravity, which we will cover here in the full GR equations of motion. There is the angular momentum part, which is also the same both in the classical and the Newtonian gravity theory. The difference that we find in the GR potential is first there's an overall constant. It will turn out that the constant does not matter for considering orbits because we will take the derivative of the potential. So the constant is just an overall shift of where your zero energy is. But more importantly, there is an additional term that couples together the gravitational part, GM, and the angular momentum part, L squared. And it's this term that is not present in the classical theory, and it is really this term from which we expect any actual changes from the GR calculation with respect to classical Newtonian mechanics. So if this term was absent, general relativity for circular orbits in a Schwarzschild geometry would give exactly the same orbits as classical Newtonian mechanics. Let us now investigate the possible orbits, possible circular orbits in Newton gravity and Einstein gravity. If we want to consider circular orbits, that means that the particle is on a circle with radius r. The radius r does not change if the orbit is an actual circle. So that means dr by d tau is actually 0. We can look for stable, or we want to look for stable orbits in addition to this. There could be unstable orbits, but we want to look for stable orbits that don't decay. In order to have a stable orbit, we need to find a minimum of the potential. For classical Newtonian mechanics, we can just derive this straightforwardly. We do the derivative of the classical potential with respect to the radius. If we do this, then we find two terms, gm over r squared minus L squared over r cubed. These have to sort of sum up to 0. So we can solve this equation for r, and we find that for Newton gravity, we have stable circular orbits for a radius of the particle that's given by the angular momentum squared over g times m. Not surprisingly, we find that for Newton gravity, all orbits are stable for all values of n. So basically, if I specify the angular momentum of a particle L in orbit around a mass m, then I can change L continuously, and there will be an associated radius for which the circular orbit of that particle is stable. Now let's redo the same calculation in Einstein gravity. To this effect, we have to take the derivative of the potential that we found for our GR equations of motion. We'll get two terms that match exactly the Newton potential, and then there's the additional term that's specific to general relativity. If we set the sum of these three terms equal to 0, we can again solve for r. We find a quadratic equation for r. If we sort of rewrite this equation up here, we can solve this equation. The equation solution is given by the following equation here. So there's a term that is in front, it's L squared over 2gm. And then we have a square root here. And the square root basically indicates that there are stable orbits for a range of values of angular momentum. But if the angular momentum gets too small, in particular, if this term here gets smaller than 3 times L squared, or if L squared over 4g squared m squared gets smaller than 3, then the argument of the square root will be negative. The square root will produce an imaginary number, and that just indicates that there is no more a real radius for stable orbits. There are no more stable radii when the angular momentum of the particle becomes too small. So this condition here just means that for a stable circular orbit in Schwarzschild to exist, the angular momentum of the particle has to be bigger or equal to square root of 12 times g times the mass of the central body that the particle is orbiting around. I will call this angular momentum LC for critical angular momentum. Particles with angular momentum less than that will not have stable orbits. Okay, so for GR, then there is a minimum angular momentum. L is LC squared GM. And there is an associated minimum radius for particles having this particular angular momentum. This radius is just LC squared over 2GM. And if you plug in this value for LC, that radius comes out to be 6 times GM. This radius is known as the innermost stable circular orbit, or ISCO for short. And that's basically a very useful quantity to know in general relativity. So you should compare this innermost stable circular orbit with respect to the Schwarzschild horizon, which is located at 2GM. And you find that ISCO is exactly 3 times the Schwarzschild horizon in a Schwarzschild geometry. A little sketch of circular radii or circular orbits in a Schwarzschild geometry then looks like this. So if we have some Schwarzschild geometry where the horizon is down here, so that's 2GM, then ISCO basically is out here at 6GM, and outwards from ISCO there can be other stable circular orbits. But if the angular momentum of the particle gets to be smaller than the critical momentum, then all orbits below ISCO will just decay in some sort of spiral motion, and the particle will fall into the central body that is creating the gravitational field. And that concludes the present lecture.